The silicon diode shown in the figure has a barrier potential of 0.7 volt. Okay, there will be a no forward current flow through the diode if VDC in a volt is greater than. See, they are asking what is the value of VDC, due to that there will be a no forward current. See, the circuit diagram is looking like this. Okay, this is a VDC by 2, this is a 500 ohm, and this is a diode, and this is a 2 volt given. It is given in the question that the barrier potential of 0.7 volt, means we have to replace, means this is a non-ideal diode, means we have to replace with this, it's a 0.7. Okay, and they are asking what is the value of VDC, that there will be a no forward current, means you have to, no forward current means the diode is reverse bias. No forward current means the diode is reverse bias, open circuited. Now what does mean by 2 volt? 2 volt means this. Okay, at this point to ground there will be a 2 volt. Now apply the KVL in this loop. It will be a -2 plus 0.7 plus, see, this is open circuit, means the current flowing through the 500 ohm is 0, then plus VDC by 2 equals to 0. Therefore the VDC by 2 equals to 2 minus 0.7, it will be 1.3, and the VDC will be 2 into 1.3, it will be a 2.6 volt. 2.6 volt. Therefore the option D is the right answer. Option D is the right answer. The differential amplifier shown in the figure has a differential gain AD equals to 100 and the common mode gain AC equals to 0.1. If V1 equals to 5.01 volt and V2 equals to 5.00 volt, then V0 in a volts up to 1 decimal place is, see, the differential amplifier, it is a differential amplifier, but it is a op-amp. Okay, and we know that what is the output in a practical op-amp. What is the output in the practical op-amp? We know that the output in a practical op-amp is given by VO equals to VD AD plus VC AC. We know that, see, AC is given to you, that is a 0.1, and AD is 100, differential mode gain is 100, common mode gain is 0.1, and it is also given V1 equals to 5.01 volt and V2 is 5 volt. Okay, now first we have to calculate the differential input VD and common mode input VC. Means VD will be, we know that it's a V1 minus V2, and the VD will be 5.01 minus 5, it will be 0.01 volt, and VC is, we know that the V1 plus V2 divided by 2, it's a 5.01 plus 5 divided by 2, that is a VC equals to 5.005 volt. 5.005 volt. Now see here, VD, what is VD? VD is 0.01, AD is 100 plus VC is 5.005 into AC is 0.1. Therefore the V0 will be, after calculating this, the V0 will be, see, this will be a 1 and this will be a 1.5005, therefore it will be a nearly equals to, sorry, this will be a 0.5005, therefore it will nearly equals to 1.5 volt. 1.5 volt. Okay, 1.5 volt. The figure shows a phase locked loop the output frequency is locked at f0 equals to 5 kilohertz. Okay, the value of f1 in kilohertz is, see, this is a diagram in which this is a phase detector, low pass filter, voltage control oscillator, and there will be a frequency divider of 5. Means we know that f0 equals to n into fi, f0 equals to n into fi, therefore the fi will be f0 by n, and n is a frequency divider, and f0 is given you of 5 kilohertz and frequency divider is also 5, it's a kilohertz, na, there will be a 1 kilohertz. This will be the answer, 1 kilohertz is the answer. Okay, the output V0 shown in the figure in a volt is close to, see, this is the op amp given in the circuit, and the options are -20, -15, -5 and 0. First of all, we will draw the circuit here. $10 1 kilo ohm, here it will be a 2 kilo ohm, it is plus 15 volt, it is minus 15 volt. Okay, see, we know that this op amp is operating in a inverting mode, because this input is applying at inverting mode, and this 2 kilo ohm is connected between output and inverting node, means there will be a negative feedback, and we know that in the negative feedback the VO by VI gain is minus RF by RS or R. This is RS and this will be the RF, and VO equals to, we know that minus RF by RS into VI. See, minus RF is minus 2 by 1 into VI is 10, it will be a minus 20. See, but we know that in a op amp the output will be always lies between positive Vset and negative Vset. Output will always lies between positive Vset and negative Vset. But see, this is out of the range. This is the out of the range. Therefore, we can say that means V0 is always lies between, V0 is always, we know that the V0 is always lies between minus Vset to plus Vset. Okay, but see, here it is less than minus Vset. Therefore the V0 will be minus 15 volt. V0 will be minus 15 volt only. Okay, I think all of you should understood this, because due to this the option B will be the right answer. Option B will be the right answer. The condition for oscillation in a feedback oscillator circuit is that at the frequency of oscillation, initially the loop gain is greater than the unity, while the total phase shift around the loop in degree is. See, whenever we will use the sufficient amount of positive feedback in the amplifier, then that amplifier will work as an oscillator, and it is given that by using the Barkhausen criteria. What is the Barkhausen criteria? Barkhausen criteria, it is given that the product of AV should be 1 and the phase of the entire circuit. Means, see, if this is a basic amplifier, this is a circuit, here this is not connected, this is a feedback network, and this is the output, na? Means the total phase shift, including the total phase shift of the loop is 360 degree, then only it will be a positive feedback, or 0 degree. Then only the positive feedback will develop in this circuit. By using this concept, we can say the option A is correct answer. Option A is correct answer, because there is no any 360 options given in the options, means options A will be correct, 0 degree. Okay. The 2 input voltage multiplier shown in figure has a scaling factor of 1. A scaling factor means multiplication factor, and produces the voltage output. If V1 equals to plus 15 volt and V2 equals to plus 3 volt, the value of V0 in volt is, see, this is a circuit diagram. this is V2, this is V1, this is R, this is R. Now see here, we know that due to the virtual ground concept, V plus equals to V minus equals to 0 volt due to virtual ground concept. See, this non-inverting end is connected to ground, means it is a 0, means this potential will be also 0, and this is the answer. Now we'll apply the KCL at this node. We'll apply the KCL at this node, means it will be a 0 minus V1 by R plus 0 minus V0, or we can say that instead of V0, this is 2 factor here, V0 na, means can I say 0 minus, a scaling factor is 1 given, means 1 into V1 into V2, sorry, V2 into V0, V2 into V0 divided by the resistance R equals to 0. Now see here, this R means it will be a V minus V1 by R, and I think it will be a minus V2 V0 by R equals to 0, means V1 equals to V2 into V0, V1 equals to V2 into V0, or we can say that minus, okay, minus, and if you want a V0, V0 equals to minus V1 by V2. V1, it is given that the V1 is 15 volt and V2 is 3 volt. It will be a minus 5 volt. It will be a minus 5 volt. I think all of you should understood this. Simple KCL. We have to apply the KCL only here. Nothing else. In the circuit shown in the figure, the MOSFET is operating in the saturation zone. The characteristic of the MOSFET is given by ID equals to half VGS minus V1 square milliampere, where the VGS is in volt. If the VG equals to plus 5 volt, okay, the value of RS in kilo ohm is. Now, see, Vs is 5 volt. First we will draw the equivalent diagram here. This is Vs, this is RS, this is RD, eight mega ohm, 7 mega ohm, and here it is a plus 15 volt. VDD is given. Now see, it is given in the question that the MOSFET is operating in a saturation region. MOSFET is operating in a saturation region, and the two parameters are given. Vs equals to 5 volt and ID equals to half VGS minus 1 whole square in milliampere. Then first of all we have to calculate the VG. See, this point will be the VG, and the VG will be 15 into 7 mega ohm na, in 7 plus 8, mega gets cancelled, it will be a 7 volt. It will be a 7 volt. Then we know that VGS equals to VG minus Vs. We know that VGS equals to VG minus Vs. VG is 7 and Vs is 5. Therefore, it will be a 2 volt. 2 volt. Now, we will put this 2 volt in this equation of ID. Then the ID will be half VGS 2 minus 1 whole square in milliampere. Therefore, the ID will be 0.5 milliampere. Okay, 1 by 2 or 0.5 milliampere. And we know that the current flowing through the MOSFET gate current is approximated to 0, because metal oxide semiconductor, oxide layer, due to the oxide layer the input resistance of the MOSFET is very high. Due to the oxide layer the input resistance of the MOSFET is very high. Therefore their IG will be 0, means the same current will be flowing through here. Here will be ID and here will be also ID will flow. ID will flow. We know that this voltage is given to you, means it's a 5 volt is given to you. We know the RS, means if you will apply the KVL, this will be plus and this will be a minus. We know that Vs equals to ID into RS. ID into RS. Therefore the RS will be Vs by ID. Vs is 5 volt and ID is 0.5, means R will be 10 kilo ohm, 0.5 milliampere. Therefore RS will be 10 kilo ohm. RS will be 10 kilo ohm. This is the answer. And this question was fill in the blanks. RS equals to 10 kilo ohm is the right answer. A resistance temperature detector RTD is connected to a circuit as shown in figure. Assume the op-amp to be ideal. If V0 equals to plus 2 volt, then the value of X is, see, the question is very simple. The question is very simple. Again, we have to apply the virtual ground concept and KCL. R, and this is given. It's a minus 12 volt. It's a plus 12 volt. Here is this is temperature RTD, and here its value is R in bracket 1 plus X, and here it is R. See, this is a V plus and this is V minus. Same it will be here also. Means V plus equals to V minus equals to 0. This is due to virtual ground concept. Remember this thing. And now we'll apply, here it is also 0 volt, we'll apply the KCL at this point. We'll apply the KCL at this point. See, it will be, now this current is coming, this current is incoming, and this current is, I assumed that all the currents are incoming, and we know that here the current will be 0. The input current to the op-amp is 0 because op-amp is ideal. Now see, this current is incoming at this point, means there is no any necessity that you should take the arrow at this point only. Okay, means at this node the current will be incoming. You can take outgoing also, but you have to apply the KCL properly. 12 minus 0 divided by R in bracket 1 plus X plus 0 minus V0, 0 minus V0 by R, or sorry, it's incoming now, means V0 minus 0 by R plus minus 12 minus 0 by R equals to 0, means by solving it, it will be a 12 R1 plus X equals to, or simply we can say that plus V0 is 2 volt given to you, V0 is 2 volt given to you, means it will be a 2 by R, this will be a minus n, means it will be a 12 by R. Now see, if we will take R common, this R get cancel. Now it will become 12 upon 1 plus X equals to 10. So 1 plus X equals to 12 by 10, means it will be a 1.2, and X equals to 1.2 minus 1, the X will be 0.2. X will be 0.2. Says this is a very simple question. The circuit of a Smith trigger is shown in the figure. The Zener diode combination maintains the output between plus 7 minus 7 volt. The width of the hysteresis band is, okay, see, this question, by looking the circuit diagram, the question is looking like the very tough, but see, the concept is very simple. In this question, the concept is very simple. The concept is very simple. See, this is a VZ. Okay. Now, in the question itself, it is indicated that Zener combination maintain the output voltage plus 7 and minus 7. Normal student will think that the VO will be 15 volt or minus 15 volt, 15 volt to minus 15 volt. But see, in the question itself given, or if it is not given, then also you have to find out these things. Means this Zener diode have a breakdown voltage is this. Okay, this is the breakdown voltage and this will be the breakdown voltage. Okay, see, if the output voltage is going to increase positively, means if it will be reached to the 7 volt, then this diode will be forward bias and this will be reverse bias. Means it will act as a short circuit and this plus 7 volt will appear here. It is always given in the question. And the given Smith trigger is non-inverting type Smith trigger. Then we know that the VUT, in this case the positive VSAT, VO equals to positive VSAT. Positive VSAT means it's a 7 volt. and VO equals to minus Vsat, it will be a minus 7 volt due to this Zener diode. Okay, then we know that VUT upper threshold voltage, upper threshold point or lower threshold point, it is a positive Vsat into this resistors, na, means can I shall I write directly? It will be a 7 into 0.5 divided by 0.5 plus 10. Okay, it will be a 0.333 volt. Okay, and VLTP lower threshold point will be minus 7 into 0.5 divided by 0.5 plus 10. Therefore, it will be a minus 0.333 volt. Okay, and we know that the hysteresis VH is VUT minus VLTP, or upper threshold voltage, lower threshold voltage, and it is 0.333 minus of minus 0.333, it will be a 0.666 volt. 0.666 volt. Okay, I think all of you should understood this. Very simple question. Assuming the op-amp shown in the figure to be ideal, the frequency at which the magnitude V0 will be 95% of the magnitude of Vin is. Okay, see, in this question they are asking the frequency at which the output will be the 95% of the input. Okay, see, first of all we will draw the circuit diagram. See, this is plus and minus. So 1 kilo ohm. It's a 1 kilo ohm. V0. V in 10 kilo ohm, and see, this is a 10 nanofarad. Okay, see, the circuit is very simple. The circuit is very simple. It's a nothing else. See, we can draw it easily by in this way also, and I think you will be familiar with this circuit. This is a 1 kilo ohm, and this will be the 1 kilo ohm. Okay, and here it is a plus, and here it is a capacitance is given. Okay, and here it's a V in, and here it is a 10 kilo ohm, and it's a 10 nanofarad. See, this is RC high pass circuit. This is a simple way of drawing the. Okay, now we know that the op-amp is operating in a non-inverting mode because the input is given at the non-inverting terminal of the op-amp, and there is a negative feedback. Means, can I say op-amp operates in a non-inverting mode. Non-inverting mode. Op-amp operates in a non-inverting mode. Means we know that the VO equals to 1 plus RF by R plus V plus, voltage at non-inverting end. Please remember, this is important concept. Most of the student taken that V in directly. No, see, V in is not appearing at this end directly. V plus. Okay, now we have to calculate the V plus. What will be the V plus? V plus is the V in, or we can directly say, if I will solve it, it will look like this. It's a 10 nanofarad, or simply, first of all, we will say it's a CS. Okay, and it's R. Means 1 by CS upon R plus 1 by CS. Now see, V in will be VI 1 by CS, means 1 plus SRC by CS. This CS gets cancelled. It will be a VI upon 1 plus SRC. It's a V plus. We know that the V plus equals to VI upon, put here S equals to J omega. S equals to J omega, and we know that omega is J2 pi F. Omega is 2 pi F. Now if you will put this, it will become 1 plus 1 plus j 2 pi f r c. Now see, this V plus, and we know that we will put here the V plus. Okay, simply we can say that the V plus will be Vi upon 1 plus j 2 pi 3.14 into f. You have to calculate the f into r. R is how much? It's a 10 into 10 raised to power 3. It's a 10 kilo ohm, na? 10 into 10 raised to power 3 into c is 10 into 10 raised to power minus 9. Now see, this V plus will be Vi upon 1 plus j. Multiply all this thing, this and this. I think we'll get 6.28 into 10 raised to power minus 4 farad. 6.28 into 10 raised to power minus 4 farad. Sorry, 4f frequency. Now put it here. We know that the VO equals to 1 plus RF, 1 plus 1 by 1 into V plus. We'll put here VI upon 1 plus j 6.28 into 10 raised to power minus 4 frequency. Okay, and we know that VO equals to 95% of VI. 95% of VI means, can I say VO will be 0.95 VI. Put here the 0.95 VI equals to 2 VI upon 1 plus j 6.28 into 10 raised to power minus 4 f. Now see, we can take the magnitude of this also. There is no any need to do this because we need the frequency. There is no any, we need not the phase. Means 1 square it will be same, and it's a j.628 into 10 raised to power minus 4 f square. Okay, this Vi gets cancelled. Now it will be here, see, 1 plus 6.28 into 10 raised to power minus 4 f equals to 2 by 0.95. Sorry, 2 by 0.95. Therefore it will be 2.105. 2.105. Now this 1 plus 6.28 into 10 raised to power minus 4 f equals to 2.105 square. That is, it will be at 4.431. 4.431 means 6.28 into 10 raised to power minus 4 f will be this. We'll subtract this one from this. It will be a 3.431. 3.431. It's a square. Now we have to take it's a square. Now it will be its root. Okay, I think all of you should understood this. Therefore the f will be under root 3.431 divided by 6.28 into 10 raised to power minus 4, and the f should be 2.949 kilohertz. 2.949 kilohertz. In this way we can solve. See, the calculation is lengthy, but the numerical is very simple. Okay. Quantum efficiency of photodiode. Ratio between the number of liberated electrons and the number of incident photon is 0.75 at 830 nanometer. Given Planck's constant H equals to 6.624 into 10 raised to minus 34 joule. The charge of the electron is E equals to 1.6 into 10 raised to minus 19 coulomb, and the velocity of the light in the photodiode is 2 into 10 raised to power 8 meter per second. For an incident optical power of 100 microwatt at 83 nanometer, the photo current in a microampere is. Okay. See, the responsivity in a photodiode is given by R, and it is eta E. Eta is the efficiency, and this efficiency is given to you. Okay, efficiency is given to you, and it is given that we know that this is to be calculated by using 0.75, okay, divided by the Planck's constant, or simply we will multiply the charge first, 1.6 into 10 raised to power minus 9, it should be a 19 divided by 6.624 into 10 raised to power minus 34 into 2 into 10 raised to power 8. What is the 2? 2 is the cm, okay, into at 83 nanometer, means it will be a 10 raised to power minus 9. Now if you will solve this, it will come 7518.11 into 10 raised to power minus 4. Now see, the R will be IP by, we know that IP by P naught. IP is a photocurrent. Therefore the IP will be R into P naught. Okay, R is 7518.11 into 10 raised to power minus 4 into P naught is given, optical power is 100, P naught is optical power, and it is given that 100 microwatt. 100 into 10 raised to power minus 6. I think it will be a 75.18 into 10 raised to power minus 6 ampere, means it will be a 75.18 microampere. 75.18 microampere.